Hello, welcome to Synthetic Data from A to Z with the MDClone Atoms platform. Today, we're going to give you an overview of synthetic data and then do a deeper dive into how synthetic data are created. I'm Dr. John Morrow, Senior Vice President and Physician Executive at MDClone, and I'm speaking to you from New York. I'm joined today by my colleague, Noah Zamstein. Noah?
Hi there, I'm the Senior Data Scientist at MDClone, and I'm speaking to you from Beersheba, Israel, the headquarters of MDClone.
Thank you, Noah. I'll start with part one, where I'll describe the basics, the what, why, and how of synthetic data, and then Noah will return for part two, Synthetic Data 201, the advanced view of how synthetic data operate. So let's answer a few questions about synthetic data. First of all, what are synthetic data? Well, synthetic data sets contain none of the actual individuals from the original data set, but they do maintain the same statistical characteristics as the original population across attributes and within subgroups. That allows you to do analyses of the synthetic data set as if they were original data, but without revealing any of the identities of the individuals from the original data set. Importantly, the synthetic data set keeps the same format as the original data. They look the same. They have the same shapes, the same columns, the same rows, the same densities. And therefore, they have the same suitability for analysis, but without the privacy concerns because you do not maintain any of the original members of the original population. It's important to recognize that synthetic data are not the same as de-identified data. They're both a form of anonymized data, but they're different, and I'll describe that in a moment. On the left, you see a representation, a cartoon of an original data set, in this case with 9 individuals. The individuals vary in their shapes and sizes, in their clothing, in their genders, and this is representing a larger population. On the bottom, you can see some descriptive statistics for this actual population of patients. Let's say there are 935 individuals with a mean age of 37.5, standard deviation 1.68, and so on. And also, other than these continuous variables of age, weight, and hemoglobin, there are some discrete variables like what color are their pants. You'll see that in this case, the most common pants color is blue. On the right of your screen, you see a synthetic data set that was computationally derived from the original data using the MDClone software. Again, this is a cartoon representation, and Noah will describe in a moment the actual process for doing this. In the synthetic data set, if you look with sort of squinted eyes from far away, it looks like a similar shape of the population. It has approximately the same number of people. They're distributed in a similar way in terms of heights and weights and genders and clothing. But when you look at it closely, the individuals are not the same. You don't see the gentleman on the far left in the striped shirt. You don't see him anywhere on the right. But the synthetic data set, again, has the same sort of shape and overall properties as the original. The number of patients in the synthetic data set, again, it's not exactly the same. It's not meant to be, but you have 950, so it's approximately the same size. And the descriptive statistics, both for the continuous and the discrete variables, age, weight, and hemoglobin, and clothing color, are very similar to the original population. They are statistically the same as the original population. You see that in the synthetic population, you have an age of 37.8 with a standard deviation of 1.71. And in the original population, they're very similar. Now, this is a smaller population. We have fewer than 1,000 members of this population. As the numbers go up, of course, the statistics would be able to match the original more closely. But statistically, these would be the same population when you're looking at them from the larger view. Here is a spreadsheet representation and a graphical representation of the same populations. And what's important is if you look at the spreadsheets, notice that the shapes of the spreadsheets are the same. They have the same columns, they have the same kind of rows. They have, if you look at sort of how many trues and falses there are in the allergy column in this case, it's it's the same, and it looks the same. If you look at the ranges, just sort of overall of ages and cholesterol levels, they also look the same. And indeed, if you look at, there's a linear regression model at the bottom, and if you look at the a scatter plot with a linear regression model, and if you look, the formulas are very similar in the original and synthetic populations, and the overall layouts are the same. But if you look at the scatter plot and look at the dots, you don't see the same identical dots. The population is the same, but the individuals that comprise the population are different. And especially when you look at outliers, you'll see that the outliers are not reproduced. And that's important for reasons that, that Noah will describe in the second part. Now, that's synthetic data. Let's just compare that quickly to de-identified data, because de-identified data is a concept that's been around longer, and you may be more familiar with de-identified data. Synthetic data are not the same as de-identified. We have our same original population on the left, but now on the right, we've de-identified them by obscuring some of their distinguishing features. Again, this is a cartoon. In reality, in a de-identified data set, you either remove the safe harbor identifiers like name, social security number, telephone number, dates of service, and so on. But what we're showing here is that we have obscured the population so that while there is a one-to-one correspondence, that first person is the guy in the striped shirt, but you can't identify who he is because you've removed his facial characteristics and his fingerprints and exactly what shoes he's wearing, for example. The problem with this, although you do maintain the descriptive statistical properties throughout, you've lost information. You've removed granularity. And so if you wanted to make an observation in this population, for example, about brand of shoe, you have now lost that because you have obscured the shoes. And we'll give a more realistic example later, but that's the general idea. Let me continue and you'll see another manifestation of this. If you take original data, a picture of an elephant, and this elephant represents a population of pixels, if you will, or a population of wrinkles on the elephant's skin, characteristics of these individual wrinkles that create this entire picture of an elephant. With de-identified data, what you've done is that you have removed the granularity of the information. You wind up with something that you could tell is an elephant, but you would not be able to, for example, tell how long the elephant's trunk or tusks are, because you've obscured those features enough that you cannot recreate it. You can't see the elephant's eye shape. You actually, in this picture, you can barely see where the eye is. And that's happened because you've removed information in an effort to de-identify this elephant. With synthetic data, on the other hand, you still have the level of granularity. You still show the wrinkles. You still show the shape of the eye, the length of the tusks, the length of the trunk. But when you zoom in on this and you look at the pixels that make up this individual or the wrinkles around the eye, you could see that the information is not the same. You don't have a one-to-one correspondence of pixels. What happened here is that we recreated an elephant based on the pixels that made up the original elephant to give the overall impression, the statistical package, if you will, of elephant. So why use synthetic data for clinical research? Why is this helpful? Well, synthetic data maintain the variables of interest and their intervariable correlations, and that's important. If there is a correlation between 2 or 3 or more variables in an original population, then the computationally derived synthetic data set that comes from that original population will likewise maintain those correlations. And just as importantly, if there are absent correlations, if there are poor correlations between variables in the original population, the synthetic data set derived from that original population will likewise show poor correlation between the same variables. There's no need to remove data elements with synthetic. You don't have to remove zip codes, for example. You don't have to remove dates of birth because there is no one-to-one correspondence like there is with de-identified data, so patients cannot be re-identified. This allows you to validate hypotheses before seeking approval to use the original human subject data. Often, and actually always, in order to use actual human subject data, you need to seek permission, for example, from an IRB or an institutional review board or an ethics committee. And because synthetic data do not contain any actual individuals, in almost all institutions, it has been determined that there is no need to seek ethics or IRB approval prior to using synthetic data, because those are not actual humans within the synthetic data set. So that allows you to maximize data utility while protecting patient privacy. This is a cartoon representation. This is not meant to be a scientific graph, but just to give you an idea that there is constantly a trade-off between privacy on the y-axis and utility on the x-axis. You can have, if you think of it, you can have a data set that is so private that it is absolutely useless. It has no utility. You could get rid of every piece of information except, let's say, the row number, and have no columns, or have all the columns blurred. There's not much you can do with that. On the other hand, you can have a data set that has no privacy because you have everything just open, and that is very useful. But you can't do that because privacy is paramount always when dealing with patient information. Traditional approaches tend to fall along the diagonal in the middle, where there's a trade-off from more privacy, no utility, to more utility, no privacy. With synthetic data, you're able to maximize utility with maximal privacy because, again, there's no one-to-one correspondence with actual patients, but you have the utility because you've maintained the statistics and the statistical properties, the overall shape, and the correlations within the population. So how do we do this? Noah will get into this a little bit more deeply, but at a high level view, you derive statistical models from the original data. MDClone derives statistical models from the original data. And then the models are used to generate the synthetic patients. You find the overall shape of the data, and then you fit points to fit those data. You do not maintain any one-to-one correspondence between members of the original and the synthetic data sets. And here's a diagram of how this is done. This comes from an article. I'll put up the link to this article toward the end of the talk, but this comes from a paper that was written by Dr. Randy Foraker at Washington University in St. Louis, validating the use of synthetic data and using a handful of clinical use cases of varying descriptions to show the utility of synthetic data. But what Dr. Foraker drew in her paper was, on the left, this is a representation of, in 2 dimensions, of an original patient data set, both as a scatter plot and as a distribution graph. And the first step of MDClone Adams' generation of synthetic data is to do what's called a kernel estimation. You draw an estimated distribution, or a heat map, if you will, of the data. And you do this in every dimension. We're showing it here for simplicity in 2 dimensions. You then sample new data points in order to create the purple dots, which are brand new. Those didn't exist before. You're creating them on the fly in order to match that heat distribution and therefore the original patient population. So you wind up with a new population that is extremely similar and statistically the same as the original population. But as you saw, the data points were created de novo on the fly, and they don't represent actual individual patients. So let's switch gears to something a little fun. Here is a spreadsheet. It's got many rows, and it's got, in this case, 5 columns. And what is this? Well, if you look at it, it's got an X, a Y, an R, a G, and a B, a red, green, and blue. So this is a pixel map. This is how a computer would represent a photograph, for example, where each row is a pixel, a point, with an X and a Y axis, and a color, percent red, green, and blue. And this picture happens to be a picture of Mama Polar Bear with her 2 cubs on a glacier. We acknowledge Yuval Ofek for this beautiful photograph. And if you then feed this data table, consider this the original data, the representation of the original photograph, into MDClone Adams, and you ask for a synthetic data set computed from this original, even though this is a picture, these are really just data points, you get a synthetic data set. And again, it looks like the original in shape and in format. You've got X, Y, red, green, blue. The red, greens, and blues all are numbers from 0 to 1. And now what happens, you can kind of see where this is going. Let's take this pixel map and let's turn this back into a picture. What is that going to look like? And lo and behold, out of MDClone atoms, you get a data set that when you plot it as a picture, you can see this is still a mama bear and her two cubs on a glacier. But you notice a couple things going on. Let's put the two pictures side by side, the synthetic data set on the right from MDClone and the original on the left. You'll notice that some of the detail is obscured or lost. Some of the specific identifiers, like look at this little guy's eyes and snout, and this little guy's ears, and mama's paw print. Even the text on the image here, you can see, or the very sharp contrast between glacier and fur. Those are lost because remember, none of these original pixels were recreated. So you lose the very fine individual pieces of detail, but you keep the overall very much so. You know that this is text, you know that this is bear, you know that this is glacier, and you could even, you can make conclusions about relationships within this data set. In this case, you can easily see that the bears are being cuddled, the cubs are being cuddled by the mama. You can see that the siblings here are holding each other. So you still get the sense of the population, what the image conveys, without revealing anything about the individuals, the specific paw print, the specific arrangement of pixels in the snout and the eyes of the cub, for example. So with that, now that you have graduated from Synthetic Data 101, I'll ask Noah to return and take it away from here with the more advanced view into Synthetic Data 201. Noah?
Thank you, John. I will try to give a deeper dive on synthetic data. What is it good for and why it could be a game changer, especially in the healthcare industry, where data access is becoming increasingly more challenging, and at the same time, the demand for quality data is growing. So as John described, synthetic data is fictitious data that mimics real data. The roles of a synthetic data set do not correspond to real people. Hence, it is sometimes referred to as non-human subject data. This data looks like real data and also preserves the statistical properties of the real data, which it tries to mimic. For example, if 20% of diabetes patients in a healthcare organization experience a heart failure event within the next 5 years, synthetic data is expected to reflect this. For the purpose of research and inference on populations, synthetic data aims to provide high utility or similarity to the original data across all types of multivariate relationships. And this makes synthetic data a great candidate for training, data sharing across organizations, discovery, and population management. There are two main buckets of synthetic data generation methods: rule-based generation and data-driven generation. Rule-based generation methods follow a specific set of rules that try and capture relationships between events. In theory, this could allow limitless generation of patients with every possible combination of clinical characteristics, including rare diseases, with no privacy concerns. By definition, these methods do not rely on the availability of real patient data, and therefore obviate the requirement for data sets from which to derive the synthetic patients. However, in order to faithfully describe realistic clinical courses, these rules must cover everything from visits, measurements, procedures, background diagnoses, medications, gaps in care, claims data, and clinical outcomes, and all their intricate dependencies in a realistic clinical setting. Now, this task becomes unscalable very quickly. In addition, nothing new can be discovered using these data sets, which was not already coded in the rules. So, for example, a group of patients reacting differently than others to a new drug. Finally, these methods are susceptible to generation of clinical inconsistencies, like pregnant males, incorrect proportions, or medical artifacts. The other family of methods, which are real data-driven, rely on real data sets collected from real patients for the generation of synthetic patients. Now, a model is built which captures the multivariate distributions and relationships between variables. For example, the plot here shows a nonlinear relationship between X, Y, and Z. The blue dots represent real data, and the yellow dots represent synthetic data. If f of y and x is analytically known, then we could generate yellow dots at will by choosing more values of x and y and calculating f of x directly. Of course, in a realistic data set, the distributions are much more complex and do not follow analytical formulae. Producing high-quality synthetic data, in the general case, depends on how closely the multivariate distributions can approximate the original underlying distributions. Generative adversarial networks, or GANs, is a popular type of a deep learning architecture for generating synthetic data from complex multivariate distributions. This architecture contains a generator, which is a neural network, which takes random data as input and generates a synthetic data set. A second neural network, called a discriminator, outputs a score describing how well the synthetic data is to the real data. It is similar to the real data. This is a computationally extensive process and does not always converge. The synthetic data should match the real data closely enough, but not too closely, such that the same types of analysis can be performed on the synthetic data. These plots demonstrate how similarity between the original data in red and synthetically derived data in blue might be presented. For the numerical variables, age and creatinine, we can examine the shape of the distribution depicted using a violin plot and a box plot, which shows the quartiles of the distribution. The distributions are very similar, but not identical. For categorical columns, we see the frequencies of the different categories, with here warfarin being the most frequent. You'll notice the word censored as the top category, which I will get to in a few slides. Univariate distributions, of course, do not tell the whole story because they reveal nothing about the synthetic data's ability to mimic relationships between variables. We therefore calculate the pairwise correlation between each pairs of variables in the data set. This value will be the x coordinate of each data point in this correlation plot. We then calculate the same correlations in the synthetic data, and this will be the y coordinate. If all these correlations are similar between the real and synthetic, we will find all the points to lie along the y equal x axis, as in this figure. The most challenging analyses are, however, those involving several variables together. In this example, we show chlamydia rates by zip code for each year, overlaid on a map. The color of each zip code corresponds to the rate of chlamydia in that zip code, where darker color indicates higher rates. Next, we plot time to heart failure for 3 levels of admission BUN results. The green lines represent results from 5 different synthetic data sets, all generated from the same real population. The dotted line represents the 95% confidence interval for the real data set. The third example shows the result of a multivariate model predicting severe COVID outcomes in admission based on 40 variables, including comorbidities, lab results, and demographics. Whatever the method of choice for generating synthetic data, its ability to protect the privacy of individuals in the real data must be ensured. As an extreme example, the best utility would be achieved by merely copying the records in the original data set, but this would of course violate the privacy of all subjects. Even if all direct identifiers were removed, individuals would still be identified. So for example, if they have a unique combination of identifiers, if I happen to come across a subject in a synthetic data set who is a bread scientist, and this data set happens to contain HIV results, I will potentially learn this result even if no other identifiers are accessible to me. Similarly, even if in my town there are 200 bread scientists and 200 people who drive a Tesla, but only one bread scientist who drives a Tesla, I might learn new facts about him and him only. As a more clinically relevant example, this screenshot shows a typical overview of a query generated in MDClone's Adams platform. At this stage, the user is just about to generate a synthetic derivative whose columns are listed here. In order not to violate the privacy of individuals or small groups of patients, our algorithm looks for combinations of categorical columns which are unique to few individuals. In this data set, the city of the patients turned out to be identifying for a lot of individuals. Hence, the city name has been censored or redacted from the data set by substituting the word censored instead of the original value. This way, we can still use the other types of information from these patients, except their city. We can see that the other categorical columns are much less identifying, as only a small proportion of them has been censored. I'd like to close with the following example of a picture of a doctor holding a $1 bill. So as John described, a picture can be converted into a tabular data set where the columns are X, Y, RGB, and the rows are pixels. The original photo and the synthetic photo look very similar and tell the same story. A doctor is wearing a white robe and a stethoscope and is holding a $1 bill in her hand. But when I zoom into the bill, you still notice, you will notice that the identifying information like the serial number and the letters have been changed to the point that we can no longer read them. We can still tell it's a $1 bill. We roughly see the number 1 in George Washington's face, but we have not been exposed to the identifying details. And with this, I'd like to thank you and thank John for his introduction.
Thank you, Noah. And I hope that I'm confident that now that you've had both the 101 and the 201 introductions to synthetic data, that you have a better understanding of what synthetic data are, how they're different from de-identified data, how they're created, and what some of the clinical and research utility can be. And thank you, Noah, for providing that information. Let me just also put up a couple of resources that you can seek. This is the paper that I mentioned earlier from Dr. Foraker and her group. It's called Spot the Difference. It was in JAMIA Open in the end of 2020. And it gives a wonderful, very understandable overview, not only of synthetic data, but also of 3 clinical use cases for synthetic data. And I highly recommend this paper to you. Another very good paper also comes from Washington University in St. Louis, and it is a predictive modeling paper where a predictive model was trained on synthetic data to predict outcomes for heart failure. And if you take a look at this paper, it also gives now an understanding that you can even use a synthetic data set to train a machine learning model and then use that model on the original data from which the synthetic data in the training set were derived. It's a really powerful concept, and this paper goes into it in depth. Finally, on the MDClone website at mdclone.com/research-publications, there is a full library, constantly updated, of research papers that are done using synthetic data and using the MDClone Adams platform. So it's a great place to get more information and do a deeper dive. With that, I'd like to thank Noah for her participation today, and to thank you for your attention. and for your interest in MDClone atoms and in synthetic data. If you would like to arrange a demonstration of our software, please visit mdclone.com/demo or send a note to my colleagues in our sales department at sales@mdclone.com. Thank you for your attention today. Bye-bye.
Thank you.